Hi, this is Keeley, and we're going to talk about the modified Atwood machine and solve some problems with this device, finding acceleration with both friction and non-friction, as well as algebraically. We've got our usual cast of characters. We've got the weight of the object, we've got tension, we've got friction. We also have normal force in there. We've got acceleration, and we got the mass. And we're trying to figure out, usually in this video, we're going to find acceleration. Maybe in another video, we'll find something else like friction or a mass. But today, mostly we're going to stick to finding acceleration. So, we'll be talking mostly about kinetic friction in that case. But let's start off with this one problem that's not really an Atwood machine, but looks like one. So on this, we've got a string is holding this, which looks like an Atwood machine or a modified Atwood machine, in place to this wall. And we want to know the tension in the rope right here. We want to find the tension right there. Well, that's different than finding the tension of this Atwood machine while it's moving. This is actually holding it in place. So that means that string is preventing this, the weight of this, from moving that. And so the tension of the string would actually just be equal to the weight of that second mass, M2 down here, which in this case is 5 kilograms. I'm going to use 9.8 for gravity. So the tension in that rope is 49 newtons because it's holding still. Now, usually in a problem like this, they'll say that rope is broken at some point, and then it sets the system into motion, in which case you'll find the acceleration, which we're going to do on the next page. So this one is a modified Atwood problem where we're going to find the acceleration and the tension in the string. And we're going to start off with, we got a 10 kilogram mass on the table, 6 kilograms off the table. Every now and then I have students go, well, it's not going to move because that's smaller than this. But in this case, there's no friction. So any force will cause this to move, because any force will cause an acceleration because there's nothing to hold it back, because we're going to say the friction between the block and the table is negligible. So no friction. So let's draw the free body diagram of this. So to start off with, we're going to have weight on this one pulling down, and then the string is lifting up on it. Since it's a force in a string, we call that a tension. We got a string pulling this way. That's again a tension, and this tension is the same as that one. That comes in handy later on. And since there's no friction, well, we don't have any force restraining it, but we're not done with the forces on this one. This one will also have its own weight, and it'll also have a normal force from the table supporting the block. And so that's the free body diagram for this one. Now getting into how to solve this problem. Now the way I do it is a little bit different. I do kind of an alternate method of solving these problems. The regular method you see in textbooks is they'll do the equation for all the forces on this, the equations for all the forces on this, and set them equal to each other, and then solve for whatever they want to. Usually setting it equal because these tensions are equal to each other, and doing it that way. That gets kind of messy sometimes. If you can do it that way, that's awesome. I'm going to do a slightly different way. I want to use this method. The force or forces that's making it move is got to equal the forces on the system. That's just my little phrase that I use to remember this by. So, what's causing this system to move? Well, it's the weight of this mass over here. So, it's the weight of that second mass. So this is mass 1, that's mass 2. And it's causing the whole thing to move, the whole system to accelerate. So that's equal to ma, but that mass is the mass of both things put together at some acceleration. So if we do this, that's really m2g equals m1 plus m2a. And if I want to solve for the acceleration, I just need to divide both sides by this. So acceleration is going to be equal to m2g over m1 plus m2 when I move that underneath. So now, let's go ahead and put numbers in it. I solved it algebraically. That's great. Usually that's very nice if you start things off, but let's put the numbers in. So from here, m2 is 6, and gravity is 9.8. m1 is 10, m2 is 6, and we're solving for A. So I want to go ahead and 6 times 9.8 gives me 58.8 equals 16A. Divide both sides by 16, and I get an acceleration of 3.68 meters per second squared when I round it off to 2 decimal places. Okay, so we got the acceleration. Now, let's figure out the tension. And I usually like to find the tension in the rope right here. Okay. So if we do that, find the tension. Let's think about what that looks like over here. So we've got MA equals the sum of the forces that's affecting its motion. Well, since there's no friction, the only force on it that's pulling it is the tension of the rope. And so MA, well, the mass is 10, and the acceleration is 3.68. So that means, if I go over here, that the tension is going to be 36.8 newtons, is the amount of force in that rope, because this rope is just pulling that block. Remember, ropes only pull, they don't push. If a rope pushes, it's not a rope, it's a stick. So that rope, string, whatever this is pulling, and so it has to pull with that force to move that block at that acceleration. All right, let's try one with friction, and this time I'll actually go ahead and put in the numbers and won't worry about solving it algebraically. We'll do that later with another problem. Okay, so this one is pretty much the same setup, 10 kilogram mass, 6 kilogram mass, but this time there is friction between the table and the block. And the coefficient of kinetic friction for this setup is 0.2. And so I want to again find the acceleration of the system and the tension of the string. This time when we do the free body diagram, we've got tension there, which matches the tension over here. We've got the weight of this block. We have the weight of this block. We have a normal force for it. And now there is going to be a force due to friction. The force due to friction always goes against the motion of the object, or that it goes against the way that object should be moving. It's always the thief there. So I want to start off with the same type setup, the same saying that I was using before. Forces that's affecting the motion is equal to the forces on the system. Okay, the system is both these masses put together. So the 10 kilogram mass plus the 6 kilogram mass being accelerated at whatever. We're going to figure that out. The force, well, the force is the weight of the second block, but that's being held back by the friction on the first block. Well, mg is just mass times gravity. Force of friction is equal to mu times the normal force. Now for this situation, that's m2. This is the normal force on 1. Well, if this is a flat level table, then the normal force equals the weight of that object. So that is actually equal to mu m1g. Now we can assemble things. So let's put in the numbers there. So weight, mass times gravity, that's the second block, so it's 6 kilograms times 9.8. Friction, well, that's going to be 0.2, the mass of the top block, which is 10, again, times gravity. So that goes in over here, so 0.2 times 10 times 9.8 equals, add that together, that's 16a. Now we got everything, we just do the math. So 6 times 9.8 minus 0.2 times 10 times 0.8. This whole side is 39.2 equals 16a. So I'll divide both sides by 16, and we get an acceleration of 2.45 meters per second squared. So it was the same setup as last time, but now there's friction. Well, my acceleration has to be smaller because the other one, the acceleration was 3.68, and that was with no friction between this top block and the table. So any friction is going to slow that down to this. Now let's figure out the tension on that block, or in this string for that top block. So again, tension, well, it's MA equals the sum of the forces on it. And that force is the forces that actually are affecting its motion. So it's the tension and the friction. So MA equals tension minus the force of friction. Well, I'll move it over here. Well, this mass, remember, this rope is pulling only that mass right there. So the mass is 10. Acceleration is 2.45. Tension we don't know, but friction is this. Let's go ahead and calculate that up there since I didn't do it before. And that is 19.6 newtons. And so that's going to be 10 times 2.45 equals tension minus 19.6. And let's go ahead and do that. Right. So 10 times 2.45 plus, because we're going to move that over, 19.6. So the tension in this rope is going to be 44.1 newtons, which is then greater than it was on the previous problem. The previous problem, the tension was 36.8 newtons. So this system, that has to pull harder because it has to overcome that friction, that kinetic friction in this case, that's trying to hold this block back and keep it from accelerating. So we need a little bit more force. Although I kind of did it before, let's solve one algebraically. And let's do something like this. Let's say M1 is equal to, I don't know, let's say 3 M2s. So M1 is 3 times the masses of M2. Let's see what we get there. So let's solve this algebraically first. So force that's making it move equals the force on the system. What's making it move is the weight of this one. So that's M2G. The system is both masses have to be moving together at the same rate because they're tied together with a rope. So M1 plus M2A. Now we can solve for A. A is going to be equal to, move that underneath, M2G divided by M1 plus M2. But we have a thing where M1 is equal to 3 times M2. So we can substitute this in for M1. So if we do that, A equals M2G over 3 M2 plus another M2, 3 there plus that one, and that's going to be equal to M2G over 4 M2, because 3 M2s plus another M2 makes 4 M2s, but the M2s cancel, and so that acceleration of that system is going to be 1/4 of g. In other words, take 9.8 and divide by 4, and that's what the acceleration would be. So that's the nice thing about solving things algebraically. If you get things in place, then maybe you can cancel some stuff out, if you're lucky. What if there is friction? This one didn't have friction, but what if we do have friction? So for this one, we've got M1, M2, same modified Atwood setup. If we try to do the free body diagram, that tension is the same as this tension. We've got the weight of this one, weight of the first block, the normal, because it's sitting on the surface, and we got a little bit of friction, trying to mess things up. Again, we'll solve it algebraically. The force that's making it move or affecting the motion is equal to force on the system. Okay. Well, the system is both things have to be moving together, so it's always M1 plus M2A. What's making it move is the weight of this minus the friction on this one holding it back. So we have M2G minus force of friction is mu times the normal force, which if we're on a flat level table is equal to the weight of that. So mu M1G. That's really small, but hopefully you can see that. So for this one, we pull that over, mu K, because it's kinetic friction, the mass of that top block times gravity. Now we've got some options on how to do things. I'm finding acceleration. I do want to clean this up a little bit, so I'm going to go ahead and do this. I want to say M2 minus mu K M1, and I want to pull that G outside, equals M1 plus M2A. Then I want to divide by the M2 plus M1. So A equals M2 minus mu M1 G divided by M1 plus M2. And that will be the acceleration of this system with friction. And then you could substitute in numbers for M1 and M2 to actually calculate what the acceleration is. All right, thanks for staying with me for this one. It's been a long one, but now we can find the acceleration of an Atwood system. Tune in again, and we'll do one with maybe 3 blocks, or maybe one where we have to find the friction if we happen to know the acceleration. Anyway, thanks for watching. Goodbye.